So today what I want to talk about is two papers. I want to talk about graph convolutional networks, which is this paper by Thomas Kipf and Max Welling. And then the second paper I want to talk about is how powerful are graph neural networks, which is going to cover a framework called graph isomorphism networks. So these are interesting because they're two very different paradigms of graph neural networks. So in the case of graph convolutional networks, essentially it's what I call the like matrix multiply framework. Like you multiply matrices to make some prediction. GPUs are great at that. So as long as you can fit those matrices on a GPU, then you're good to go. And however, graph isomorphism networks use a different paradigm called the gather scatter paradigm, and I'll explain what that means in a second. Gather scatter. So yeah, I mean, without further ado, let's just get started. So in this paper, there's sort of like a few key ideas that they want to introduce. So the first one is that they introduced this thing called graph convolutional networks, which is heavily inspired by regular convolutional networks from Vision. The idea is that you want to build a local representation of each node using primarily its neighbors. So this is very similar to in convolutional networks. So you build a representation for a pixel using its neighbors. It's not really a pixel, right? Because it's a compressed version of the image. And then they show a bunch of experiments on this on a data set called the citation network. I think it's called CAT or something. So regardless, like what's sort of interesting and what I want you to think about here is that like what do I mean when I say like it's all matrix multiplication, right? So um, on one hand, like when you have an adjacency, like when you have a graph, right, you can represent this using an adjacency matrix A, right? And so let's say this is the, you know, like let's say if this is saying for like let's say this is position 1 2, this means there is an edge between them, right? The thing is though, this graph is going to be mostly sparse because most edges, especially if you consider large graphs, are not going to be connected to each other. And then in this paper, they also have some node level features, which they call X. So you can think of these as like, well, each of these graph in the node is going to have some features, like maybe probability of having COVID, number of friends they have, how likely their paper is to be accepted. So you have like a whole bunch of features. And then on each row here, you're basically going to have like the features for person I, for node I. And so it's via some form of matrix multiplication between A and X that we're really gonna like get the basically be able to make some sort of prediction on nodes, for which we do not have a label, right? Because again, if this was just about like node level classification, you have all the features that you need about a person, you don't actually need to run a graph convolutional network. But the fact that the in this even in this in this vector v, which is a column vector because it's data, you're gonna have some features that are full, like let's say your line means they have something, but others like it'll just be sparse, right? So it is an example, like this is why they use the phrase semi-supervised, right? Because like it's not unsupervised, but at the same time you are missing labels from your training data. It's not like you're training on this and then given another graph. Um, and then they're saying it's classification, but you could imagine it could be regression or generation or whatever. And then graph convolutional neural networks, which is the main framework we're discussing today. So if you go here, they say, okay, well, we're gonna build this regularized loss by looking at aij. So this is essentially given a node I, all of their neighbors j. Take the sum between, take the norm between the current representation of that node with all of its neighbors. So f is basically some neural network. And I believe this is mentioned here somewhere. Where is it? So yeah, so f can be thought of as a neural network, but it's really any sort of differentiable function. Think of it as a neural network. Um, and so the assumption here is that connected nodes will have more information. And so you can also end up rewriting this where you can say, okay, well, I want f of x transpose, and then let's see, what is this delta exactly? Uh, so the delta is d minus a, so it's the unnormalized graph Laplacian. of an undirected graph. Oh, I see. Um, so basically, this is just like using like some intuition from spectral graph theory, but essentially one will be, so D, I believe, will be your degree matrix. So yeah, let's do this. Like delta is going to be D minus A, right? So this is your adjacency, and then this is your degree matrix, right? So you may ask, like, what does degree of a matrix mean? Let me show you. Yeah. So basically, the degree matrix is going to be like it's a matrix of the same size as the adjacency matrix, and for each vertex, it's going to count the number of times an edge terminates at that vertex, right? So uh, let's see. So what is the intuition behind this? Okay, regular graph. Yeah. So this is all Fan Chung. Like I studied with I T8 for Ji Chung Graham. Like I T8 for her husband. But she's also like an insane mathematician. Like they're sort of a power couple. Um, let's see. So number of edges. Yeah. So it's contained. So then that is the number of edges attached to each vertex, and it is used together with the adjacency matrix to construct the Laplacian matrix of a vector. And so, like, what's sort of interesting about the spectral graph theory business is that essentially by taking this delta, you can study like how a matrix, like how a graph is, by just looking at its degree and adjacency matrix. And so the idea is that like it's just like an alternate representation, but a graph is sort of like this graphical thing. It's a data structure. But if you can turn it into like a more mathematical structure, like a matrix, then you can study it. And so we're gonna just see like how they do this in this paper, I assume. So they encode the graph structure directly using a neural network and train on a supervised target L0 for all nodes with labels, thereby avoiding explicit graph-based regularization in the loss function. So conditioning f on the adjacency matrix of the graph will allow the model to distribute gradient information from the supervised loss and will enable it to learn representations of both nodes of both with and without labels. So their contributions are twofold. First, we introduce a simple, well-behaved layer-wise propagating rule for neural network models which operate directly on graphs and show how it can be motivated from a first-order approximation of spectral graph convolutions. And secondly, we show how this form of graph-based neural network model can be used for fast and scalable semi-supervised classification of nodes in a graph. So experiments on a number of data sets demonstrate that our model compares favorably uh, and efficiency measured in walk clock time against state-of-the-art methods for semi-supervised learning. Okay, great. So yeah, so this is the algorithm actually. Like I think this is what shows up in the spectral code base. But I guess it doesn't make too much sense if you haven't read the paper. So yeah, so they're saying that in this section will provide a theoretical motivation for a specific graph-based neural network that we will use for the rest of this paper. So we consider a multi-layer graph convolutional network with the following layer-wise propagation rule. And so what is H? So, okay, let's see. What are we missing here? So we have the degree matrix, right? So we have this degree matrix. We have the adjacency matrix. We don't know what W is and we don't know what H is. So let's see if they explain. So A is the adjacency matrix with added self connections. And IN is the identity matrix. Okay, so just a quick question on my side, like why do we add self connections? Just a quick question. I guess it should be explained further down the paper. So DII is equal to, so so WL is a layer specific trainable weight matrix. Sigma is an activation function, sure, such as ReLU. Okay, that's fine. And so H is a matrix of activation in the nth layer. So it's of size n times d. So h0 is equal to x, and the following show that the form of this propagation rule can be motivated via a first order approximation of localized spectral filters on graphs. Um, okay, so let's just take a look at this form a bit more closely. So we take the degree matrix. So here, like this whole d minus half, d minus half times a. This is again just some way of saying d squared times a. So we take the square of the degree matrix, multiply it by the adjacent. So it's close. I think there's like an easier way to read it, even though it's not correct. It's just like an intuition. So you're saying it's dA, and then, so what was h again? Yeah, so then basically the activation h times w, right? So this is sort of an interesting form, but as you can see, it's all matrix multiplies. Um, these, I mean, they will be of, so like let's say in the, like where's, oh yeah, so x is going to show up here, like at the very beginning. It's the activation for the very first layer. Okay, and they're saying this is motivated by spectral graph theory, and then they're going to do some crazy stuff with Fourier. So let's just see if this makes sense or if it's going to be too complicated. So they consider spectral convolutions on graph defined as the multiplication of a signal with a filter g diagonal of theta parameterized by theta in the Fourier domain. So you're taking g and then convolving it with x, and then you get u g theta u x. And so u is a matrix of I eigenvectors of the normalized graph Laplacian. Normalized graph Laplacian. Okay, this is fine. Um, basically, like let's say so. Yes, so it's saying like instead of taking the filters directly, you can take the eigenvectors of the graph Laplacian, and you also get like basically a convolving filter, and then they can simplify it using a Chebyshev polynomial. Okay, that's all fine and good. They simplify it with the Chebyshev polynomial and then some complicated thing. Okay, so really it looks like they keep referring to this Hammond paper. I think this is like where all this stuff looks like is explained. So let's just take a look at Hammond et al. Oh wow, this is like sort of looks like foundational paper, like over 1,000 citations for a graph paper. All right, I mean obviously I don't think we have time to read all of this. But let's just take it for granted, right? Like we can, assume that that paper is correct. Like basically what we're saying is we can approximate graph convolutions using Chebyshev polynomials, and once you add the whole thing back in, then you have basically the issue with this algorithm as is that it takes big O of n squared to multiply by the eigenvalues and finding eigenvalues, I believe. But what's the complexity of finding eigenvalues? I think it should probably be at least. Oh wow, it's a cube. I see. Oh, this is cool. And I guess useful to think about. Like, yeah. So you see here, all of these are like kind of the classic slow things, like big O and cube, like matrix inversion. Singular value decomposition is a bit more reasonable. Finding the determinant is, looks like hella slow, one n by n matrix. Uh, yeah, so basically anything sort of interesting starts taking cubic. And then here, one n by n matrix and one n by n. So n by m, yeah, and matrix multiplication. So really, what is fast here? It looks like everything with matrix algebra is slow. Uh, and yeah, Fourier transform is like a lot simpler. I mean, complexity-wise, not not to understand the algorithm. Um, okay, that's cool, I guess. And so let's see what they do then. So a neural network based on graph convolutions can therefore be built by stacking multiple convolutional layers of the form from equation 5. And so each layer followed by a pointwise nonlinearity. Now imagine we limited the layerwise convolution operation to k equals 1. Uh, Therefore, linear function on the graph Laplacian spectrum. Oh, okay, interesting. So they make a couple of simplifying stuff. So they're like, we take the layerwise convolution operation to k equals 1. Okay, so then you're basically saying at every point the layerwise convolution uh is going to be just like theta and t, and then what's L here? Okay, L is also this complicated. I feel like I'm missing some background here because like they seem to really be blasting through this without explaining it. I think it's gonna be the Hammond paper. This is really important. I have to read this paper. I think here. Um, okay, so let's keep going. So they do this linear reformation of GCN and they approximate lambda max is equal to 2. Uh, Further to address overfitting. Okay, okay. And so we can generalize the definition of a signal with f filters or feature maps as follows, where theta is now a matrix of filter parameters and z is the convolved signal matrix. This filtering operation has complexity epsilon fc, and ax can be efficiently implemented as a product of a sparse matrix with a dense matrix. Oh, I see. Okay. So I think this is sort of the like it's basically like et cetera, et cetera, et cetera. But this is sort of the main algorithm, right? And we talked about this already. So you have a theta, you have which is your model parameters. You have x, you have d, which is your degree matrix, and then you have your adjacency matrix. And so it sounds like I would expect in Spectral then they would compute the degree matrix uh, for you. Let's just double check that, right? Because like how long? Like let's see, for example, if I go to Spectral, let's say layers, and then convolutional. Yeah, let's say graph convolutional networks. So let's see. Degree matrix doesn't doesn't look like it at least. Okay. So then like if you want to do classification of this, I think like this is definitely the harder part, right? Which is like just the operation. But then having introduced a simple model, then what you can do is you're getting it back to the problem. And okay, so we consider a two-layer GCN for semi-supervised node classification with a symmetric adjacency matrix. Um, yeah, so that happens, I guess, if like let's say this is citation. Yeah, so like basically undirected. So this is like symmetric means undirected. And so they first calculate A with this as a pre-processing step. Our model then takes the simple form of f of xa as just the softmax of A ReLU ax w, right? And so W is the input to the matrix, the little layer, And so then they evaluate the cross entropy over all labeled examples where YL is the set of node indices that have labels. The sum of all indices in labels. Oh, I see. So the parameters are trained using gradient descent, and they perform batch gradient during descent using the full data set for every training iteration, as long as the data set fits in. Using a sparse representation for A, stochasticity is introduced via dropout. Okay, interesting. Yeah. So basically, they're saying like, well, because in their case the data set isn't huge, it fits in RAM, so uh, even fits like on like an accelerator's memory, so they can just like feed the whole thing immediately to an accelerator. And once you do that, like it's fairly straightforward. And so then they say, okay, so there's a bunch of related work with zoo, Laplacian regularization, label propagation, semi-supervised embeddings. Um, Inspired by the skip-gram model, deep walk, which learns via the prediction of local neighborhoods of nodes. Yeah, so I've actually talked about these quite a bit. So there's, for example, like this format called SMILES, which people use in chemistry. And so basically, given some sort of molecule, let's say as a graph, you turn this into a sequence, and then you basically feed it to a transformer. All right, so this is one way of doing this. Another way is, you have a graph, and then you feed this to a graph convolutional network. So you have two ways of basically solving the same kind of problem. The thing is, like, about transformers though, is that, like, I mean, yeah, they seem to work fine, but it does seem useful to generally be able to encode that, I am indeed working over a graph, as opposed to saying it's a sequence when it really isn't. All right. So neural networks that can work on graphs, they report unsquared capacity, convert graphs into local sequences that are then filled to. Yeah, so this is a paper I read like months ago. I think now I even had a stream about it. Um, which fast localized convolutions. We consider the task of transductive node classification uh, with significantly larger scale, and that a number of simplifications can be introduced to improve the scalability and classification. And so I guess, like, in terms of like once you have this, right, so like let's say here, um great, so yeah, we have this hidden layer, we have this output layer. It's going to give like a bunch of activations, and then you do like a soft max over all of them to see which one is most likely to be the prediction that you're looking for. Yeah, this is what the soft max is about. um and then, yeah, so it's interesting to me here, like so they use a relu for AXW, and then they use another soft max here. So really, I think that the trick is basically here. Like, so basically, this is, like, once the above is done, this is now easy. And I think here, to get this, there was a couple of tricks. One was the basically the spectral graph theory reformulation. And then the second part was the linearization of it, right? So instead of having these like this polynomial approximation, they just made a linear approximation, and that way you can evaluate a convolution at every layer very efficiently, which is, I guess, like something that was new relative to other kind of work. Um, so let's see some results, for example. So for example, here, like, looks like the largest network that they use had 65,000 nodes, but 266,000 edges. Um, Symmetric adjacency matrix, random graphs, experimental setup. So they used a two-layer GCN, and they citation, we optimize the hyperparameters on Quora and use the same set of parameters for sites here in PubMed. So we trained all models for a maximum of 200 epochs, training iterations using Atom with a learning and early stopping with a window size of 10. And we stop training if the validation loss does not decrease for 10 consecutive epochs. Um, yeah, so I've mentioned this before, but like, I mean, I've tweeted about this, but early stopping is, maybe the single most important regularization trick that you can use. Um, always use it. And anytime you do an early, like, let's say in Keras, it works. Like, you can just say something like, it's like a Keras dot callback like, you early stop, and then it's something like, let's say, 10 iterations, it hasn't improved, then just stop. So this is absolutely crucial that you actually implement this in your actual experiments. So here, for example, they further compared against the iterative classification algorithms. Okay, so this is like the other benchmarks. Uh, so here, for example, they've said, okay, well, this is first off the results that we got. And they're saying their results are better than everyone else's. So I guess the main competitor was Planetoid. Uh, yeah, it looks like these are roughly sorted, right, by how good they're. No, they're not. I mean, yeah, they kind of are actually. Yeah, I think they're just sorted by on average how good they are across these three tasks. What was Deep Walk again? I do like how they made it very clear what the other algorithms were here. I think it was in related work. Deep Walk, Deep Walk. Walk. Okay. So here, for example, they're saying like with the Chebyshev filter, this is the propagation model, and then you take the first order model. It's gonna. It's funny that it's making the performance better. You'd expect it to make it worse, but then they're saying, okay, well, we take a single parameter and then we do the renormalization trick. I actually really like the way they presented results here. I like how they're referencing it to different equations. I think this is a very important chart. So let's just like go see if, okay, oh, actually they even had it here. So like the propagation model was this, and then they simplified it by saying x theta. Okay, so they moved x theta outside, and so now this is just the identity matrix with d minus half, d minus half. Okay, so they just factorized it. That's fine. And then here, what they did was that uh, oh, I see, I see. Okay, so instead of having this complicated expression on top of x theta, they're just like, okay, well, it's just going to be x theta. And then here, what they did was the renormalization trick, and that let them remove the in. I see. This is kind of cool. I like the way they presented the results here. Here we report results. We can on a GPU and CPU only implementation and TensorFlow, and we summarize the results. So CPU versus GPU. Oh, interesting. This was exactly my observation. How like where is GPU? Lol. And then yeah, so seconds per epoch, and it doesn't feel like, I mean, even it's just funny that the GPU is just straight up slower, indicates out of memory error. Yeah, that's what I ran into as well. It was kind of a funny error to run into because I actually never run into out of memory on GPU before. Like never an issue. Like is like because you just take mini batches, right? Um, Comparison. Okay, so propagation of feature information from neighboring nodes in every layer improves classification and compares it to methods like ICA, where only label information is aggregated. And so we have further demonstrated that the proposed renormalization model offers both improved efficiency and better predictive performance compared to a bunch of other naive limitations. Uh, okay, yeah, so they're saying we don't know what to do with large graphs, so you need to take approximations of densely connected neighborhoods of them. Uh, they do not support edge features and is limited to undirected graphs. Uh, but I think this was fixed in subsequent work. I just forget the paper that fixed this, so maybe I'll just note to self which paper supported uh, edge features. I'm not sure, like, but I do know in Spectral at least I have definitely used it. And so linear limiting assumptions. We assume locality for GCN with k layers and equal importance of self connections versus edges to neighboring nodes. Okay, they're saying we may want to add a trade-off. Uh, sure, yeah. And so we've introduced a novel approach for semi-supervised learning that is based on a first-order approximation of spectral convolutions on graphs. And so experiments on a number of network data sets suggest that the proposed GCN model is capable of encoding both graph structures and node features in a way that is useful. Yes. What about the relation to the Westphaler-Lehman algorithm? Node embedding with the random weights. Even an untrained GCN model with random weights can serve as a powerful feature extractor for nodes in a graph. So as an example, consider the following three-layer GCN model. All right. So these are random weights, and then so we apply this model on Zachary's Karate Club network. This graph contains 34 nodes connected by 154 edges. So we take a featureless approach. Oh, I see. Interesting. So basically, even uh, with untrained weights, GCN gives decent embeddings. That's kind of interesting, actually. So here, okay, I don't know what this was about. Experiments on model depth. Okay. So we investigate the influence of model depth on classification performance on five-fold classification, carry the model number of layers. Uh, Interesting. Like data sets, both results are obtained with 2 to 3 layer models. Interesting. Yeah. So basically, perf uh, tanks for more than 5 layers. Most GCNs are actually 2 to 3 layers. So that's actually was a fascinating thing for me, like, cause like I'm used to like let's say images, like it's like ResNet 50 or ResNet 100 or whatever. It's like always 100 layers of transformers, like something similar, and probably even more. Uh, so what I found interesting here is that if you actually look at a lot of benchmarks, like they all use a tiny number of layers, and I guess this is sort of the maybe the paper that motivated some of the stuff. Um, this is a really nice paper, actually. I thought it was like very clear. I think the only difficult part about it was this initial part where they the sort of the spectral algorithm, but uh, basically, like I think like the way I'm gonna think about this is like, well, I really just need to go read the Hammond paper to understand this first part because I don't think they explain it in sufficient detail here. But the way to think about it is that, like, well, at every point, your layer is basically going to be taking the square of your degree matrix times your adjacency matrix times your activation times your weights at that feature, and then this is your forward propagation model. You can train this with automatic differentiation to get the reverse model and get your gradients. It's semi-supervised because not like let's say in this case, like most of your like let's say in the case of small graphs it's actually supervised, right? Because you have some graphs that are labeled and some graphs that aren't, and then you take a graph and you make some sort of prediction. Whereas here you're taking in the same graph. It's not like between training and test your graph is going to change. So really, what changes is that like some nodes may be added. So basically, the graph does change, but it's more that like whenever a node gets added, it doesn't have any features, and that's why it's semi-supervised. That said, you could always come in and have some sort of UI where a data scientist comes in and manually labels stuff. But this is sort of like I think a good example of a framework that would benefit from having human in the loop, for example. And I think what I really liked was this is such a cool table actually. Like I really love this. Here is a complete summary of the things we did and how it changes the performance on different data sets. And I guess it's like back in the day when you could, like let's say here, how many experiments would they have run total, right? So if they have one, two, three, four, five, 6 different tricks on 3 different data sets. Oh, I mean, so yeah, so it's just gonna be 18 experiments. So that's somewhat reasonable, right? Like, and here, uh, well, I think here they may have used like their competitors' papers. Like, otherwise, it's again like 6 times 4. Like, I'm surprised we they didn't show Nell here at all. Like, probably the results aren't that great. And I also really like this graph here showing how like you actually don't you get really diminishing returns from a GPU. So I think this will be really important in any sort of future work where an accelerator wants to claim that they're better. I think this will be crucial. All right, so I think at this point I'm ready to go on to the next paper. Uh, let's see here. I'm having like internet issues with my laptop, so I can't see chat like I would usually do. Okay, looks like it's working now. Okay, great. So let's just go over the second paper now. So maybe actually no, I want to do did I summarize everything? Yeah, so I said this. So basically I'm gonna, again maybe put some important. I think this Hammond is important. Then softmax is important to figure out like how to actually use this thing. And then this is basically important that using the callbacks and stuff. Uh, and then this, and then this, and then just the summary I think is very good. All right, we're in good shape to move on, so let's just do it. So for context, like I don't know who these I don't know who Stephanie and Kayulu are, but I have seen Weihua's name. He's one of the maintainers of the OGB graph framework, and I believe Jura is his advisor, who's a scientist at Pinterest that works on graphs and probably a bunch of other stuff. And so let's take a look at this. So graph neural networks are an effective framework for representation learning of graphs. And GNNs follow a neighborhood aggregation scheme, where the representation vector of a node is computed by recursively aggregating and transforming representations of its neighboring nodes. So many GNN variants have been proposed and have achieved state-of-the-art results on both node and graph classification tasks. However, despite GNNs revolutionizing graph representation learning, there is limited understanding of their representational properties and limitations. So here we capture a theoretical framework for analyzing the expressive power of GNNs to capture different graph structures, and our results characterize the discriminative power of popular GNN variants such as graph convolutional networks and graph sage, and we show that they cannot learn to distinguish some sort of simple graphs. So we then develop a simple architecture that is provably the most expressive among the class of GNNs and is as powerful as the Weisfeiler Lemon graph isomorphism test. And so we empirically validate our findings on a number of graph classification benchmarks and demonstrate that our model achieves state-of-the-art performance. Okay, that was a mouthful, so let's sort of discuss it. So they're saying like that they're saying that these other GNN variants like GraphSage and GCNs, which are the most popular, at least as of 2019, right? Um, However, they can't distinguish some sort of simple graphs, and so I guess like they're going to show us examples of when it fails. They're referring to this thing called the Weisfeiler-Lehman graph isomorphism test. I also saw a reference to it in the first paper, but I'm not sure what it does yet. So let's just quickly check that. And the last thing they say is that we try some benchmarks on graph classification. That's important to mention because when they say graph classification, they mean small graphs because you can't. It's very like you don't need to classify a large graph. You would need to classify nodes in a large graph. Whereas on a small graph, you would need to classify, like, let's say it's a molecule. I guess, again, the examples I think about are molecule for small and then social network for big. So let's just, I guess, before we get started, I'm curious about this lemon graph isomorphism test. Lemon graph. Of course, it's by Michael Brownstein. Uh, okay, so it's a polynomial time solution for the graph isomorphism problem. Oh, I see. So it's based on like coloring iteratively. It's ridiculous how many like I can't think of any accessible graph tutorial that wasn't written by Michael Bronstein. It's like crazy. Okay, anyway, let's just get back to this. So learning with graph structured data such as molecules and there's like blah blah blah. Uh, so GNNs follow a neighborhood. So after k iterations of aggregation, a node is represented by its transformed feature vector, which captures the structural information within the node's k-hop neighborhood. Uh, the representation of an entire graph can then be obtained by pooling, for example, by the summing all the representation vectors of all nodes in a graph. Okay, so just remember, so here, like, as before we were talking about large graphs, and here they're talking about something slightly different. So let me just, visualize what this is actually trying to say. So imagine that, you have this GCN that looks something like this, right? Uh, like a graph, right? So the first step is you're gonna say, well, let's say I want to aggregate all nodes that are in a neighborhood of one of me. So basically, this node will take in data from this here. So this node will take in data from here. This node, you'll take data from here, sorry, here. This node will take data from here. So then you end up with sort of like these different like neighborhoods, and each of these will have like a certain number associated with it, like an activation. And so what you then do is you pool them. So for example, you say, okay, well, great, I'm going to take the max of basically these three things, or I'm going to take the average of these three things, and then that lets me just output a real number. And so let's say for a regression or for a classification, it could just be like 0, 1, or just something that's in a step in general. So they mentioned like there's like a billion different like like graph aggregation schemes and pooling schemes, and that is true, by the way. Like you'll see this quite a bit in the You'll see this mentioned quite a bit, like if you look at any of these libraries, like Spectral, that sort of talk about this. Okay, so they represent a theoretical framework for analyzing the representational power of GNNs, and we formalize how expressive different GNN variants are. Um, okay, and then our framework is inspired by the close connection between GNNs and the Weisfeiler-Lehmann graph isomorphism test, a powerful test known to distinguish a broad class of graphs. Similar to GNNs, it updates iteratively and knows features by aggregating feature vectors of its feature neighbors. And what makes the test so powerful is that its injective aggregation updates that maps different node neighbors to different feature vectors. And our insight is that GNN can have as large of a discriminative power as the WL test if the GNN's aggregation scheme is highly expressive and can model injective functions. Okay, this is a big mouthful, but I think what we need to do now is uh so wait, so this paper I need to read this paper, I think, straight up. So I think this paper I have to read. Or just maybe Michael's Bronstein's tutorial. Right? So to mathematically formalize the above insight, our framework first represents the set of feature vectors of a given node's neighbors as a multiset. Sure. A set with possibly repeating elements. Then the neighbor's aggregation in GNNs can be thought of as an aggregation function over the multiset. Okay. Hence, to have a strong representational power, a GNN must be able to aggregate different multisets into different representations. Uh, we show that GNNs are at most as powerful as WL test. We establish conditions on the neighbor aggregation and graph readout functions under which the resulting GNN is as powerful as the WL test. And we identify graph structures that cannot be identified by GCN, and we precisely characterize. We develop a simple architecture, graph isomorphism network, and show that its discriminative representation power is equal to the power of the WL test. Interesting. Okay. All right, this is good stuff. So we begin by summarizing some of the most common GCN models. Okay, so here graph neural networks. You're saying we have like I like they completely change the. So yes, you have a graph to W of our theoretical framework. I see. So of a graph neural network, formally the kth layer of a GNN is, uh, yeah. So the kth layer is the input from the is a representation from the k minus one layer, like the activation over all the neighbors, and it's a set. And then that set is aggregated in some way using some pooling mechanism. And so this combined pooling mechanism is basically either a sum or an average or just some other operation that's similar. In the pooling variant of GraphSage, the aggregate has been reformulated as you take the ReLU of this, and then in graph convolutional networks, it's W times the mean IC. Yeah, I love this actually. This is sort of a I'm gonna call it so just like this is the framework of GNNs. Like this is nice because then as long as if it's this, you can be like, well, I'm gonna plug in different algorithms. This is like some nice, a nice formula for like I've done this graphically, but like this is like a nice summary. Um, for node classification, okay, it's a readout, and then okay, so then they discuss the test. Whether two graphs are topologically identical. And so this is a challenging problem. No polynomial algorithm is known for it yet, apart from some corner cases. It's an effective and computationally efficient test that distinguishes a broad class of graphs. Its one-dimensional form, naive vertex refinement, is analogous to neighbor aggregation in GNNs. And it iteratively aggregates the labels of nodes and their neighborhoods and hashes the aggregated labels into unique new labels. And it decides that two graphs are non-isomorphism if at some iteration the labels and the nodes between the two graphs differ. So based on this test, a proposed WL subtree kernel that measures the similarity between graphs, and it uses the counts of node labels at different iterations of WL test. Okay, so there's sort of like, I guess, like more probabilistic frameworks for this thing to compute it even faster and even more efficiently. So a multiset is a generalized concept of a set that allows multiple instances for its elements. So a multiset is a two-tuple where S is the underlying set of X that is formed from its distinct elements, and M from S to N, it's bigger than 1, gives the multiplicity of the elements. So a maximally powerful GNN would never map two different neighborhoods. This means its aggregation scheme must be injective. Thus, we abstract. So I think injective meant reversible. Oh, I see. It like yeah, okay, sure. So provided that whenever f of a is equal to f of b, then a equals to b. Oh, I see. So it's not that it's invertible. It's just that if the output on any two neighborhoods are the same, then it's the same neighborhood. So you never map the neighborhood to the same. Uh, oh, I see. So then this gives them, I guess, the argument by which they're going to start saying whether two graphs are similar is that like they're just going to keep looking at the mappings of neighborhoods, and if they differ, then they are indeed different. And so first we characterize the maximum representational capacity of a general class of GNN based models. So let G be two non-isomorphic graphs. If a graph neural network maps G1 and G2 to different embeddings, the Weisfler uh, Lehman graph isomorphism test also decides that G and G1 are not isomorphic. Proofs are all in the appendix. Okay, that's cool. Uh, so now let's say A be a GNN with a sufficient number of layers. A maps any graphs that the Weiss assess as non-two different embeddings if the following conditions hold. A aggregates and updates node features, and A's graph level readout, which operates on the multi-set of node features, is injective. So assume the input feature space is countable. Let G be the function parameterized by GNN's kth layer. The range led the space is also accountable for all. Discussing an important benefit of GNNs beyond distinguishing different graphs, that is capturing similarity of graph structures. Uh, okay, so now what's the graph isomorphism network? So having developed conditions for a maximally powerful GNN, we develop a simple architecture that provably satisfies the conditions in theorem 3. So this model generalizes the WL test and hence achieves maximum discriminative power among GNNs. So there exists a function such that h of x is equal f of x is equal to unique for each multiset. X is countable. So we use great. So then what is it? We can make epsilon a learnable parameter, then a graph injective network is represented by this thing. So I'm gonna skip the derivation and just like look at this and try to convince ourselves that this somewhat makes sense. So they're saying we take a multi-layer perceptron from, okay, so something times the activation at the previous layer plus the sum over all neighbors of the activation at the previous layer, and then you learn it with an MLP. So because MLPs can represent the composition of functions, we do not need MLPs before the summation or one-hot encoding. We can make epsilon a learnable parameter. Sure, yeah, so it's just like a way to weigh one or the other. Thanks to the universal approximation theorem, we model in the first iteration, we do not need MLPs. Oh, I see. So basically, as opposed to taking, instead of, I mean, this is sort of a long-winded way of saying something pretty simple. Like, this is really what they're saying. They're saying when it comes to the pooling, so when it comes to aggregating information, it looks like they're going to do it in a fairly similar way. Like you look at all of like node level activations and you add them up, and this can be as complicated as you like. Like you can look at a like the larger neighborhood you look at, the slower this will be, but the better the representation. But then instead of just taking the sum or the average, they learn an MLP for it, and so that is just net better, and it's also injective. Um, so just straight up better. I think like the issues with sums and stuff is that they tend like you tend to lose information. Uh, okay, and so then they're saying a hidden layer for a graph can just be a concatenation of a hidden layer or replace across all iteration layers. Okay. All right. So I guess now what they're doing is they're saying, okay, well, like what is like in terms of expressive power, like let's rank stuff. So for example, looking at multisets is better than looking at a mean, which is better than looking at max. And so like I guess it makes sense, right? Like in a max you're losing more information, whereas in a mean you're keeping it across three things somewhat. Because straight up in a max, like the other things don't matter. And so here examples of that mean and max aggregators fail to distinguish between. So here, for example, mean and max both fail. Like they can't tell the difference between these two. Here, max fails, and mean and max both fail here. So these are all of the same. I see. I see. Yeah, I mean, this is really just saying like you can use an MLP for this. Like I think this is sort of a common trend I see quite a bit, where like the last layer is an MLP that takes in everything. So it looks like it's unsurprising that this is also showing up in graphs. I will say, like, even though I like the argument, I think they could have, uh, I don't know, like for example, this was I think a great explanation. I think here felt a bit rambly, but then if you look at it here, you're like, oh, okay, I see. So I think maybe, I mean, I'm just criticizing. I think like they're better writers than I am, but like if this was near the top, for example, I think this would have been like a lot clearer. So max pooling learns sets with distinct elements. Okay, so they're just thinking of several cases where they fail. Uh, training set performance. Okay, so here. So some of MLP with like the graph isomorphism networks, and here they're saying, well, the epsilon helps. Um, Not always low though. It looks like it actually reduces the performance. Okay. And then they're also saying that, but even after the performance is reduced, it does look like it beats everything. Yeah, everything on every benchmark. I'm just like slowly checking. Okay, so they have like number of nodes, number of graphs. Okay, so then they compare test set accuracies. They do not talk about the generalization ability. Yeah, I mean, that is correct. They essentially outperform the less powerful GNN variants on all 9 data sets, achieving state of the art. Uh, in this paper, accuracy of GNN is with MLP aggregation is 71 plus or minus 4.6. This research is supported by blah. Okay, so I think this is sort of going to be this is I think we're done. So basically, like the main thing I wanted to discuss, and I think a good high level summary of both of these papers is this. So in the case of graph convolutional neural networks, like what you're essentially doing is at every node, like you're building some sort of uh, local representation of it. Oh, sorry. So at every point, you're building some sort of like local representation of a node. Um, and then what you're essentially doing is you can use spectral graph theory to basically build like a linear approximation of a node's features instead of using like something as complex as the Chebyshev inequality. Effectively, what you're going to have in your formulas is going to be your degree matrix. So your degree matrix, which is the number of nodes that you're connected to, given number of vertices that each vertex is connected to. Adjacency matrix, which vertices are connected to each other. X, your feature, X, your data, and then theta is your model param. So if you're doing this for multiple layers, then you're going to also end up with some hidden layers. Typically for these networks, they'll have a few number of layers because the performance degrades quite a bit at more than 5. Uh, but essentially, the way this sort of works, and I think they make the case here really nicely uh, in this graph isomorphism paper, is that typically a lot of these networks will have some sort of like aggregation step and a combined step where you're aggregating. One is like you're getting data from your neighbors, and then two is you're figuring out how to combine this data from your neighbors, either with max or min, which are typically the most popular approximations. What they do in this paper instead is, instead of using a sort of a hard-coded pooling, they learn the pooling, they learn with the best way to combine data via a multi-layer perceptron. And then they also show how, like in general, how the mean and max struggle to learn certain kinds of graph representations. Uh, and this sort of talking about graph representations is important. Like basically, how good your model is heavily dependent on your ability to distinguish between two different graphs. And that is and this is highly predictive of your ability to say to just be able to classify a graph. Because if you can tell if two things are different, then you can tell that they're of two different classes. So the idea now is that, like, instead of using a GCN and figuring out how to combine stuff, you can just like learn this from the data directly. And it does seem like, based on the data here, that this outperforms everything else. So this is sort of really promising and actually not all that complicated. Like both of these algorithms are fairly simple to implement. You can look at their implementations on Spectral. GCNs are particularly nice because it's literally just matrix multiplication. Whereas here it's like a matrix multiplication followed by an MLP. So both of these like should be like less than 10 lines of code ideally, and a lot more to make them work and make them work efficiently. But sort of the core algorithm, that's pretty much it. Yeah, I mean, so I think that's it for me. I hope you enjoyed this, everyone. And I still need to think about what to do for another episode. But if you have any ideas, do let me know. Thank you.